So we have already discussed the feedback interconnection between two systems, and we had seen the small gain theorem in the context of feedback interconnection. So this brings us to the next topic, where we'll be specifically handling nonlinear systems where the number of inputs and the number of outputs of the system are going to be the same, and these nonlinear systems could be actually expressed as a feedback interconnection of a linear system with a nonlinear system. Okay, so consider a system of the form y dot plus let's say tan hyperbolic of y dot plus 2y to be equal to 0. So suppose this is a system that is going to evolve on its own without any input. So this system can be essentially represented as the following. So you consider the system which is, so to represent the system, consider a system which is of the form y double dot plus 2y equal to u, which means ys by us will be equal to uh, 1 by s square plus 2. Now where is this going? Okay, so what I am trying to do is, if you consider the previous autonomous system, this is nothing but y double dot plus 2y is equal to minus tan hyperbolic of y dot. So this is the system that is to be solved for. Okay, so now considering the LHS, which is y double dot of plus 2y, let that be equal to some u. So the transfer function turns out to be in this particular form. Okay, so what you have is some u coming up, passing through 1 by s square plus 2, and then suppose it passes through a derivative block. Okay, so what is the output going to be? The output of this, so 1 by s square plus 2, when it passes by that, the output is y. When this passes through this, it will be y dot. Now this y dot will pass through a nonlinear block. What that nonlinear block does, it takes a signal and gives the output as tan hyperbolic of the signal that it has taken in. So here the output is going to be tan hyperbolic of y dot, and then this is fed back as this. So this is equivalent to, or this is a representation for the system that we have taken up, right? So what you have is uh, 1 by u passing through 1 by s square plus 2 giving you y, and then you have passing through the derivative block gives you y dot. Y dot passes through this tan hyperbolic nonlinearity to get tan hyperbolic of y dot, and here in this loop as it completes, u is nothing but minus tan hyperbolic of y dot. So y double dot plus 2y becomes equal to minus tan hyperbolic of y dot. So this is what you have. So to simplify this further, this is of the form s by s square plus 2 passing through a nonlinearity, which is this, and getting fed back to the system as this. So this is what is the system, where this is a LTI system in feedback with a memoryless nonlinearity. Okay, so what is a memoryless system? Memoryless systems are systems where the output of the system depends only on the current input. It does not depend on any past behavior of the system. Okay, so for example, in this tan hyperbolic case, if I have a graph between the input u and the output tan hyperbolic of u, essentially this is going to roughly look like this. Okay, so whatever value of u is given here, the corresponding output will come out as this. Does not depend on what was the output at previous instant of time, or what was the state of the system at previous instant of time. So this system has no memory. It acts on the basis of what is happening now. Okay, so we will be discussing of systems which nonlinear systems which can be represented as a feedback interconnection of a LTI system with a memoryless nonlinearity. Okay, so what we'll be discussing is, we'll be focusing our discussion on nonlinear systems that can be expressed as a feedback interconnection between a LTI system and a memoryless nonlinearity. Okay, we'll be discussing of such a system in this particular case. Now, so we'll have a LTI system in feedback with a memoryless nonlinearity. Okay, now why such systems are of interest? Okay, why are such systems of interest? If you see, let's say that you have a LTI system. Okay, and the feedback path has a gain k in this form. Okay, and suppose this k can vary from 0 to infinity. Okay, so for a LTI system with the variation of k from 0 to infinity, we can always find, I mean, not always, given a LTI system, suppose for this gain k, if it is in the range of k1 and k2, where k1 and k2 both are greater than 0, okay, greater than equal to 0 and less than equal to infinite. Okay, so suppose for some value of k1 and k2, this feedback interconnection is stable. Okay, and we have seen such problems. Okay, so these are problems wherein we try to so k is basically a unknown gain, so you try to find out the value of k or the variation of k over which the closed loop system remains unstable, closed loop system remains stable um, for this particular thing that you have here, right? For this particular closed loop system that you have here, LTI block with the unknown gain k, right? So you can either use the idea of Nyquist plots, or you can use the idea of, you can use the notion of Ruth Hurwitz to find the range, but you can find a range. Okay, the point is you can find a range. Okay, so what does this essentially mean is, uh, let's say the input to the block k is, let's say E1, and the output of the block K is E2, or rather let us represent it as the input being phi and the output being xi. Okay, so input being xi, output being phi, doesn't matter. So let's say, suppose this is the block. Now suppose, as I said, this k, for a value of k between k1 to k2, this interconnection is going to be stable. Then essentially this means that, if this is the xi axis and this is the phi axis, then the k1 and k2, okay, they represent two straight lines, with one with a slope of k1 and another with a slope of k2. Okay, so the range k1 and k2 essentially in the phi xi axis represent two straight lines, one with a slope of k1 and another with a slope of k2. Now, for if it says that in this range, if you take a k, then the LTI system will essentially, LTI system with this feedback value would essentially be stable. Then it means that if the property, or if the characteristics of phi versus xi is such that it is also a straight line with a slope, it is also a straight line with a slope k, if this slope is k, and if you if this is the characteristic line that you choose, so that for a given xi you get a phi as a output, then in such cases the LTI system would be stable. Okay, so till this characteristics line's slope is within the range of k1 to k2, this feedback system would be stable. This is for a linear system. So this is what we have, is a linear system. Now, this interesting property here, after seeing this, Aizerman, he believed, or he proposed the following. So what did Aizerman propose? He said that if you have a LTI system which is in feedback interconnection with a constant gain k, like this, and this feedback interconnection is stable for k in the range of k1 and k2, for some k in the range of k1 and k2, then he said that if you have the same LTI system, this is the same LTI system in feedback interconnection with a memoryless nonlinearity, which I am representing through psi. Okay, if the same feedback interconnection, if the feedback interconnection with the same LTI system, and in place of that constant gain, if you have a memoryless nonlinearity, Okay, such that phi by xi lies in the range of the same k1 and k2. Okay, then this feedback interconnection is stable. Okay, so what this is trying to say is, for any value of gain, if you show that if it lies between k1 and k2, the feedback interconnection resulting in a linear system is stable. Then with the same LTI system, if the constant gain is replaced with a memoryless nonlinearity such that the input to output ratio is always within k1 by k2, then this feedback interconnection will also be stable. Okay, so if this is phi, this is xi, and suppose this is your k2 and this is your k1, then if the nonlinearity is of this form, so this is psi dot. So the green curve is representing the nonlinear relationship between the output phi and the input xi for the memoryless nonlinearity. And if the nonlinearity is such that phi by xi lies within k1 by k2, so this graphically essentially means, if you see this lines with slope k1 and k2 are forming sectors. Okay, so if the nonlinearity, memoryless nonlinearity is such that the characteristic curve, for characteristic curve representing this memoryless nonlinearity lies within these sectors that has been shown. So what sectors? So it lies within, let me just set this transparency. So it lies within this sector. Then the feedback interconnection of the LTI system with the memoryless nonlinearity will also be stable. Okay, so this is known as the Aizermans conjecture. Okay, so we'll state the Aizermans conjecture properly. The Aizermans conjecture. If the feedback interconnection of a LTI system and a constant gain k is stable for k in the range of k1 and k2, then uh, the feedback interconnection of the same LTI system feedback interconnection with of the same LTI system with memoryless nonlinearity, this such that phi by xi, or I should better say psi of psi by xi, belonging in the range of k1 by k2 will also be stable. Now, this is an important conjecture, because what this is trying to establish is, if you have a nonlinear system that can be represented as a feedback interconnection between LTI system and a memoryless nonlinearity, then you just have to find the slope, or you just have to find the range of the gains over which the linear feedback interconnection system would be stable, and that range will also work for this memoryless nonlinearity, provided this memoryless nonlinearity is lying in the sector that you have found out. Okay, so to repeat, what this conjecture is trying to say is, if you have a nonlinear system, which is a feedback interconnection between a linear time invariant system and a memoryless nonlinearity, then, and if you want to find out if with the memoryless nonlinearity the system is going to be stable or not, then the easiest way is to replace the memoryless nonlinearity with a constant gain k, and find the range of k over which this feedback would be stable, and that range will essentially define a sector within which, if the memoryless nonlinearity lies, then the original nonlinear system under consideration will also be stable. Okay, so from a linear analysis of a linear system, you can conclude about the stability of a nonlinear system. This is what this conjecture is trying to say. Okay, so we'll see how we can take this forward in the next lecture. We'll stop here. Thank you.